Hey folks, welcome back to Chemistry with Mrs. Mays. Now we're in the second part of reaction prediction, and we're going to start with combustion reactions. The first thing to remember here is that hydrocarbons are involved as the fuel in combustion reactions. And they're going to have some air, right? They react with oxygen in the air to release energy. In addition to releasing energy, we also get the products carbon dioxide and water every single time we burn a hydrocarbon. Sometimes there's impurities in there like sulfur or nitrogen, so we get other products too, but carbon dioxide and water are the ones you can count on. So let's do an example. In our first example, we'll talk about the methanol fuel that we used in the whoosh bottle experiment. So we have CH3OH plus oxygen, which is a diatomic element, so remember to put a little 2 behind it. And of course, for the products, we're just going to write the two things that are always the products, carbon dioxide and water. Now for balancing, I want to summarize our steps. To balance a combustion reaction, what do we got to do? First, fix your carbon. Make sure that your carbons are even on both sides. Your second step, look at your hydrogen and make sure your hydrogens are even on both sides. And if they're not, put a coefficient in front of your water. And then the third step is to add up all the oxygens in carbon dioxide and water and even them out on the other side. So that's what we're going to look for here. Check the carbon and carbon dioxide. I have one in my methanol over here. So I just need one carbon dioxide to balance that out. But my hydrogens, let's see, I have 3 plus 1 makes 4 hydrogens. So now I need to have 2 waters to balance my hydrogen. And now I have 2 oxygens in carbon dioxide and 2 oxygens in my water, because now I have 2 waters. So that makes 4 oxygens altogether. Since I already have 1 over here, then that leaves me with 3 oxygens that I need. So I have to use a fraction because I got an odd number of oxygens. And remember, we can't keep a fraction. Sometimes we have to use a multiplier of 2. So I have to multiply everything here by 2. So I get 2 methanols, and then 2 times 3 halves is just 3. 2 carbon dioxides, and now 4 waters. Now I have a balanced equation. Let's do one more example, and then we'll take a look at another kind of reaction. So in example 2, let's pick a different fuel. How about ethane? C2H6 is ethane. And now let's add some oxygen because it's a combustion reaction. And of course our products on the other side are going to be carbon dioxide and water. Okay, now let's balance the equation. So first, look at the carbons. I have 2 carbons in ethane, so I need 2 carbon dioxides. That balances my carbon. Now in ethane there are 6 hydrogens, so I'm going to need 3 water molecules so that I can have 6 total hydrogens here. And then if I have 2 carbon dioxides, that's 4 oxygens there, plus 3 more from my waters, gives me 7 total oxygens. Gosh, I got an odd number again. So I start with 7 halves, but we can't stay there. We have to use the multiplier, so double everything. So I get a 2, a 7, a 4, and a 6. There we go. Now we have balanced combustion reactions. Don't overcomplicate the combustion reaction. Just turn it into carbon dioxide and water and balance it. That's all. Now let's take a look at acid-base reactions. Acid-base reactions always start out like any other double replacement reaction. And by that, we mean we're going to swap the cations. The cations are the ones written first in the formula. The only thing is, in an acid-base reaction, the cation is hydronium, or hydrogen, and the other one is some metal that's attached to our hydroxide. Great. Well, let's try it out. In the first example, let's suppose that sodium hydroxide reacts with phosphoric acid. And so I swap the first two things. Sodium and hydrogen are going to trade partners. So now the sodium will partner with phosphate, and the hydrogen will partner with hydroxide. Let's check our charges to make sure we have good formulas. So first of all, sodium still has a +1 charge, and phosphate, if you look on the back of your periodic table, you'll see phosphate here has a -3 charge. That means I'm going to need 3 sodiums to hang out with my phosphate, and since I only need 1 phosphate, I don't need to put it in parentheses or write 1 behind it, it's fine. And then hydrogen hydroxide, of course, we can write as water if you prefer. Or you can leave it as HOH, because then it's easier to balance sometimes. Now let's balance this. I just put a 3 here for the sodium because of the charge. Now I have to come to the other side and make 3 sodiums in sodium hydroxide. But of course that changed what happened to hydroxide. So go back to the right and now put a 3 in front of the thing with hydroxide in it, which is your water. So now I have 3 hydroxides, but I also have 3 hydrogens. And that's all right, because over here I had 3 hydrogens on the left. So now everything is balanced. Let's do another one just to be sure that we've got this. Acid-base reactions do not always involve reacting a metal hydroxide. Sometimes the base is just a really good acceptor of protons or donor of electrons, in which case, what do? Well, same thing as before. It's the wife swap reaction. It's a special kind of double replacement reaction, so don't panic. Just swap the first two things. So now sodium gets to hang out with chloride, and hydrogen is going to hang out with carbonate. Let's check charges to be sure our formulas are written properly. Sodium has a +1 charge, and chloride has a -1 charge, so that part's easy. The hydrogen has a +1 charge, but carbonate, on the back of your periodic table, here it is, carbonate has a -2 charge. So we're going to have to adjust this formula somewhat. And now we get to the instance of the special case. If carbonic acid is formed in a reaction, it automatically decomposes. And you're probably already familiar with this. Carbonic acid is what makes your soda fizzy. So carbonic acid automatically breaks down into water and carbon dioxide gas. That's what forms the bubbles in your soda and makes it fizz. So anytime you form this carbonic acid, H2CO3, as a result of double replacement, then you have to cross it out and rewrite it as water and carbon dioxide. Now we need to balance this equation. So first I'm going to take care of my sodium. On the left I have 2 sodiums, so put a 2 out in front, and that changes my chlorine, so I have to go back to the other side and put a 2 in front of the chlorine, which also changes my hydrogen, but that's okay. I needed 2 hydrogens in my reaction anyway. And as far as the carbon and oxygen are concerned, look, I have 1 carbon here and 1 carbon here. And 3 oxygens show up over here. One of them is in the water. The other 2 are in the carbon dioxide. So now this equation is balanced. Okay, we have one more type of reaction. So let's take a close look at double replacement reactions. Again, we sometimes call this the wife swap reaction because we're just taking 2 things that already have partners and switching the cations so that we can rearrange the bonds between our elements and get something new. So, swap the cations and crisscross your charges before you balance. Now, of course, there is a stipulation. Double replacement reactions, like single replacement reactions, do not always work. In order for this to be considered an actual chemical reactions, we must have something actually change. We can't just have a bundle of ions floating around in our beaker. It has to either form a gas, that's the letter A, or a liquid, like water, or it has to form a solid. If none of those things occur, then it's not a reaction. All right, time for an example. Suppose that we combine sodium chloride, NaCl, with magnesium nitrate. And remember, magnesium has a +2 charge, so I need 2 nitrates to hang out with it. And here's what we're going to do. We're going to take our first 2 things, those are the cations because they have positive charge, the sodium and the magnesium, and we're just going to trade places. So now sodium gets to hang out with nitrate, and magnesium gets to hang out with chlorine. Notice that we always write the metal or the positive charge first in the formula. So now let's check charges to see what kinds of formulas do we need here. Sodium has +1 charge, and nitrate, let's look in the back of the periodic table. Here's our nitrate up here. NO3 has a -1 charge. So if I put a +1 and a -1 together, then this formula looks like it's just fine. But magnesium has a +2 charge, and chloride has only a -1. So we have to adjust this formula to make those balance out. Now that I have 2 chlorines on the right, it's time to balance this equation. I need 2 chlorines over here as well. And that changed chlorine, but it also changed sodium. So back we go. Put a 2 in front of your sodium in sodium nitrate, and that changes my sodium and my nitrate. Nitrate needed 2, and now I have 2. Everything's balanced. Let's take care of one more example just to be sure that we've got it. Calcium nitrate this time. And let's combine calcium nitrate with silver sulfate. So just like we did before, take your first 2. Just like we did before, we're going to take our metals and let them trade places. The metals are the ones written first in the formula. So that means calcium is now going to hang out with our sulfate, and silver gets to partner with nitrate now. Let's go back and check charges to be sure that our formulas are good. So calcium has a +2 charge, and let's check sulfate on our periodic table. Sulfate is down here. SO4 has a -2 charge. Great. And silver is here, +1, hanging out with nitrate. Nitrate is right here, -1. Oh good, look, a +1 and a -1. So these formulas don't need any adjustment. Their charges all cancel out. But we do have to adjust our reaction because I have 2 nitrates here, so I need to put a 2 in front of my silver nitrate to balance that out. But now my silver is not balanced because I didn't write this formula properly. Look, I had a +1 for silver and a -2 for sulfate. Good thing I went back and fixed that. or else our equation would never have balanced. So you got to start out with the right formulas. Okay, I also mentioned that we have to check solubility, because if we don't form a gas or a liquid or a solid, then there will be no reaction. So let's check solubility for our products. Sodium nitrate falls under the category of both alkali metals and nitrate salts, and those are both soluble, so we write an AQ because that means they dissolve in water. Now let's look at the magnesium chloride. Looks like I do not have a rule for magnesium salts, but I do have a rule here for chloride salts. Chloride salts are soluble except for silver, lead, and mercury. And I'm not pairing up here with silver, lead, or mercury. Magnesium is not one of those. So these salts are aqueous. And now, since everything is aqueous, that means we did all that work for nothing. There's no reaction here. Because what ends up happening is I mix my two solutions together and they just stay dissolved. They stay mixed together. So my beaker just has a mixture of ions and nothing ever really changes. They just float around together without creating a bond. Well, darn. We better check the other one and see what happens. So look for calcium sulfate and silver nitrate. Wait, didn't we just see a rule about nitrates? Look, nitrate salts are soluble, always. So I know this one is aqueous. Oh gosh, let's check calcium sulfate. I have a rule about sulfate down here. Sulfate salts are soluble except when they're with lead, silver, mercury, barium, strontium, and calcium. Oh good, there's our exception that we needed. That means when it's with calcium, it is not soluble, so we write an S. This is called your precipitate. And the precipitate is going to fall out of the solution. So look, something actually did change here. Thank goodness. I was worried we had done all that work for nothing. But now we have a reaction. So when you do double replacement, always check your solubility to see if anything's really going on at all. And that's it for types of reactions. We'll practice more in class.